So today you probably hear a lot from the conference about MTF, about sharpness, about screen door effects as well. And so hopefully today we'll cover all of that in a unified model and then talk about our contribution and how we apply this model into our product design that's out in the market today. Oh, by the way, my colleague Tricia and I will also give a demo later today at 5:30, just outside the coffee area. So come over and stop by. Let's start. Because we have 30 minutes, that was a burden actually. I confirmed with the organizer, and so we'll just review the challenges a little bit more and talk about some applications here. I love Steve Jobs, and he used to say that you've got to start with customer experience and work backwards to the technology, and that's certainly true. It's increasingly true for mobile devices. When we shift from TV to portables to mobile devices, your cell phone, and also ultimately your headset devices you put directly on your face, it's very easy to make mistakes, and certainly when new technology coming by, they're not always better, and particularly all experience, right? We, of course, want all the experience are better, but that's certainly challenging. So what experiences matter for VR and AR and also MR? I use this graphics language to put them into two categories. One is texture. There we have sharpness, we have a screen door effect. So that's today's topic, and hopefully we can combine both. And then we have the color accuracy, we have the color uniformity across the field of view, we have the brightness uniformity across the field of view. We have the general contrast, which is viewing glare if you're in optics field. And we also have the ghosting. It's a very typical defect for a pancake. And then on the geometry category-wise, we have a pupil swim. That's sort of a dynamic distortion behavior that, when severe, will cause motion sickness. We have orange pupil. It's very similar to pupil swim, but it's local in nature. It doesn't cause motion sickness, but it's quite annoying. Of course, we have the binocular fusion or distortion disparity, which causes, cross eyes. VAC, you probably hear about this in the past few years all the time, and field of view, dynamic behaviors, and there's a lot more. I think my team at Meta recently published some of the interesting work in color accuracy and color features in MR, also at IS&T conference last year. And the how do we mathematically model motion sickness, that's published also last year, so you can take a look. Including today, and there will be more interesting work coming out. So I want to stress that our team, our foundational motivation is about guiding the design and shipping of great products, right? And I think the metrics and models are part of it, and it's just a means. Okay, why do we care about resolution again? That is a little bit disappointing, but hopefully I can tell you more about this. In this post-retina display era, since Apple announced a retina display, why do we still care about this? I think the optics in the XR, XR means VR, MR, and AR, effectively stretches the small display to a much larger field of view. So you are definitely seeing a much larger pixels, and that's where a big part of the screen door effect. So for example, iPhone 13 display has only 28-degree wide, and then vertical that's only 14 or 15 degree. This is when you hold your iPhone, close to your face, 25 centimeters away. You're getting a very small field of view. And for VR and for AR, particularly for VR, we need a lot more field of view, right? 90 degree to start with, and we need more. So that means per angle, per degree, the pixels numbers are much lower in VR if we're using the same display. So larger field of view means lower PPD or pixel per degree. That's actually your eye's perception. You don't care about PPI, pixel per inch, right? How big the pixels are. If you push it further away, it's still very high PPD. You don't care about the pixels. So the VR challenge is here. The second challenge is we probably need 10x more pixels than the iPhone and we have to place them on a quarter size of the iPhone display today. This is just, I'm not targeting iPhone. iPhone, of course, is a beautiful product. I use it all the time. It's just, everybody knows what iPhone is, right? And, there's some Apple folks here. And of course, I'm going to show some of my images here. And this is iPhone 3GS, and it's the same display as iPhone 1. So it's 163 ppi or 28 ppd. iPhone 4 was the first one. Retina display is 56 ppd. That's also what Apple refers to. Retina display resolution is not about the PPI, right? And iPhone 13 is slightly higher, but they have a diamond-shaped pixels as shown in there, so it's not that high on paper. So VR today, we're already much denser, much higher density than any iPhone out there, but that's not enough, right? We need 10x more, and a quarter size. And additionally, for MR, if you don't know, what MR is, mixed reality. That's you're not seeing the outside directly, and that's in AR case. But for MR, if you have a camera seeing outside, and then you can capture that, and then hopefully with low delay, you can project that into the display and sense that to your eye. So more layers means more challenges. A little bit of math here, but very simple how we calculate the PPD. And if you have the iPhone case, typically the iPhone pixel size is about 50 micron. And at 250 millimeter away, you have 87 ppd. That's very high, right? And then if we place that same display hypothetically behind the lens for VR, the game is completely changed, right? And you have the EFL where you project that. You place that display at the EFL location, the effective focal length location, and then you project that virtual image further away, and you get 10 ppd. Right, so this is where a simple math to calculate how much more pixel we need. What is a good PPD? I think it depends, right? We constantly cite this number 60 PPD for 20/20 vision. Do we need that for 20/20 vision? Yes. Do we need 60 PPD or 20/20 vision for all applications? No. I'll show more next slide. Unfortunately, I think the text is very challenging. It's one of the most challenging content we have. And it's not about text legibility, but also how good the text is looking, is appearing, right? So on the bottom, this is taken from the iPhone, and taking the photo has a 56 ppd. That's a second image. Is about 20-25 human vision. And then for the video frame is 28 ppd and is about 20/40 vision. So not half, but 20/40 human vision, right? And if you do that wide field of view video from iPhone, that's 15 ppd, so 20/80 vision. So you actually, for the first point, you actually do need 60 ppd to get to 20/20 vision. Spend a lot of time surveying this. I think is interesting for the audience, but what is the landscape, right, for consumer electronics in terms of PPD and typical usage? The big axis is 15 PPD to 90 PPD, so there's a big range of consumer electronics. And if you have a typical HD or 1080p 24-inch monitor, you are getting 32 PPD. Is very productive, right? We still use the display today. I mentioned the iPhone 1, 2, 3 is about 28 PPD, and then I've been using Apple's 27 Cinema display for the past 10 years, I would say, and it's not Retina display, but sometimes you just need to enlarge the text. Retina display threshold, we typically say 56 ppd, corresponding to the iPhone 4 error. And that's on the display side, right? So for VR, we're today about 20 to 30. We're definitely on the path to make it better. On the camera side, I think this is for mobile phone camera, we typically don't talk about, yesterday we have the talk of 5 years we don't change the sensor, and we typically talk about optics limited, not sensor limited. But for MR application, we're in different games. We definitely need more pixels. For example, iPhone can only see 72 by 54 degree field of view. If MR targeting 100 by 160 ppd, we need video signal of 36 megapixel at least, right? So That's not trivial. The good thing is we don't need all this PPD for all applications, right? For photo quality, you focus more on the low range, 15 to 30 PPD-ish, and for text quality, you do need more. Of course, this depends on the font size, depending on, sometimes the font types. I think the CSF, human CSF contrast sensitivity curve had been constantly mentioned. We should be integrating frequency. We say no because a couple reasons. I think one is the content determines, what you design the product for. And the second reason is human eyes are already doing this. And if you design your product to do the same thing again, you may end up, worse results, worse performance than needed. Right, I'll give one example. Right, so the keyboard legibility. If you use your laptops, and it's very typical usage, and the legibility. If you read the text, right, it's about 5 cycles per degree. So that needs at least 10 ppd to resolve. But that's not comfortable. Right, and for that corresponds to the second or the third row of that eye chart I just showed, and it's just the same image on the right side. I just cut paste over here. For the text quality, for seeing the text very comfortably, you definitely need much higher PPD. So 5 PPD is in the center of the human sensitivity curve, but you need more, right? For different applications, you should weigh your application more than what the human is doing. One more thing is also not just about PPD, right? And I think we talked about the first one, different resolution. We also talk about, in this talk, we'll also talk about pixel shape and fill factor, right? And part of the reason that iPhone switching to, or any display switching to OLED is because they use some pentel or diamond-shaped pixels. They actually need higher resolution to get to the same perception of the result. So the shape, the fill factor is meaning the lit area of the display, how big ratio that is over the full area of the display. And typically, the larger, the better. But we all know that if we put more dense pixels, right, in LCD particularly, your fill factor will suffer. Right, and you cannot have, the transistor size cannot shrink further, and unless you were changing the architecture completely. So typically, even though we're much higher density in VR, and our fill factor is suffering. And the third one, graphics rendering, subpixel rendering, has a big effect in the end. And then the optics will blur from all over the places. And some more interesting, I think the sensors and also display is sampling in nature. There's deep meaning of that sampling phenomenon. But one interesting thing is this: if you have the signal right on a single column, you have a very high MTF, right? And then if you do a test on a different occasion and landing on 2 columns, you have a much lower MTF. How do we model this, right? And the sampling direction, and we all know that the text orientation matters, right? Different fonts also matters. The last one I also mentioned this fill factor. And here you can see that I'm not sure how you view this because the distance and the size I don't control. But typically you see the 64% fill factor is better. It's not the higher the better. So we'll show this in the demo, and you can come around and take a look. So I think, let's take a pause, right? And what are we looking for here? I think engineering challenges, we know that for VR, we need a lot higher density pixels and bigger field of view. And it's also user experience depends on the application. How do we adapt to different applications? And design challenges, not just PPD. There's fill factor, there's sampling effect. There's also the optic side. What we're looking for is a model to quantify all the factors above and the spec to guide the optical system design, right? And, I like to use this example of how do we mathematically model the motion sickness and why we do that, right? During the past decades of motion sickness research, there's not many equations that I can use to design my products. So we just invented our own, right? So in this one, optical flow is the way that we mathematically describe pupil swim. or motion sickness, but that's a 4-dimension data. How do you score that, right? And we have a way to score that. Take a look at our paper. But the goal here is very similar. We're trying to get a score. We're trying to get a model, a single score, that we can evaluate all different designs on the very right side. And then we also have a spec. We make sure all the VR products we're generating today are passing that score. It doesn't, cause people motion sick. Similar in our system MTF metric, and this is, do we have a model, a way to capture all the complex contributors we just mentioned, match the user experience quantitatively, and guide the practical system design? I'm not going to talk about the image formation in the convolution in spatial domain and in frequency domain, but that's the basis for MTF. There's a couple of very good references I put in there, but the benefits of MTF can be multiplied, right? So for MR system, it's a camera multiply VR, and the camera is a lens multiplied by sensor, and the VR is a lens multiplied by the display. You just keep adding them, right, or multiplying them. The other one is quantifiable with the spec. We can generate some sentence like this at certain frequencies. We require 20% or 35%, system MTF. We expand the traditional MTF theory to include many, many factors, including this graphics rendering. Shift invariant, this is talking about like if you land on a single column or between two columns, how do you deal with that? And it's an integral, so we can average things out. And of course, the PPD resolution, and that's the nature of sampling, pixel shape and fill factor, and optics and eye blur. That's really just one factor, right? And if we do just optical design, purely focus on optics, we're really ignoring all the bigger picture, right? Also, we have an interesting weighting over orientation because of the text and also frequency. Text quality and text legibility will be different. And again, that frequency is not about human. It's about the content itself. What can I say? We spent a few weeks on making this work and adapting the old MTF, but surprisingly, implementing this in code is not too complex. We're able to do this and being functional. I'm not going too much detail, but orientation of the text, right? And for English, we have a way to analyze for letter A, E, and small e, and what is the angular distribution is. And weighting over the usage frequency of your text, we can get also different fonts and different sizes. We can get a weighting function that we can use as part of that equation. Also interestingly, I'm learning different languages, and they are different. And so we have to, in our design, we do have to keep that in mind. This is part of our demo as well. So there are 6 images. The first row is 25 ppd. The second row is 36 ppd. So low ppd, high ppd. And then different columns means different fill factors from low to high. You can see that for low ppd 25, it's not the higher fill factor, the better. And you need this, some optimum fill factor to hit the mark. And then for the high PPD, is actually the higher the better, right? This is screen door is actually 2 effects. There's a fill factor effects, how small that hole is, and also how sparse the sampling is. And this is fully predicted by our system MTF theory, and we can plot this 3D image for PPD on the x-axis, fill factor on the y-axis, and system MTF at the z-axis. For 25 ppd, we actually have an optimum fill factor to match. And for higher PPDs, this is the higher the better. And of course, this depends on the testing frequency, the content frequency. In this talk, we won't mention why we try to focus on 15, and that's actually the focus of text quality per se. It's certainly not for graphs. Right? A little bit detail, but this is in frequency domain, what it look like, right? Humans, we don't operate in frequency domain, but this is purely just mathematical expression. The sampling effect will generate replica of the content MTF in frequency domain, and then you multiply by the pixel shape or the fill factor effect. and then you sum them up, you get this user-perceived MTF. This is the most simple, implementation, but visualizing this can be interesting. And you can see that different samplings will shrink that distance between the replicas. Fill factor will also change the shape. So in the end, it's not that simple, right? You cannot just intuitively know the higher fill factor, the better. There's an optimization there. The next one is we really want to give this, perception meaning and how we match this to the user preference. That's our ultimate goal, and we can just use this math to guide my optical design. A lot of work. This was done by my partner Tricia. And what we did is we didn't generate like high PPD VR system, but we are able to do this on a high resolution display. Just ask people to sit far away. We're intrinsically rendering 480 PPD, and of course, by doing like 10 by 10 subsampling, we can get a range of interesting PPDs we can evaluate. There's a letter E, and based on the display pixel layout, we can generate different emulations on the high density, high resolution display. And on the right side, this is an interesting graph. On the axis is the PPD. On the left side, this is a perception JOD. You can consider that as a JND, where I'm not good at explaining that. But one JND one JOD means if you present them with two cases, 75% of the population will clearly prefer one over the other, right? So that 0 and -1 or positive 1 is all relative. You can put the 3 in as 0, and then 2 will be -1. On the right side is our calculated system MTF. We didn't do any scaling, it's just directly from the math. We're able to match quite decently. If you just plot the system MTF and perception data, you can get a very good linear match over there. A couple of interesting findings here, I think, is generally, and human perception is quite sensitive, 5% MTF. In this sense, I would say this MTF is the same as the optics MTF, response to 1 JOD. And 25 to 30 PPD, 5 PPD generate 3 JODs, right? So that's the biggest gain from, investing. 50 to 60, you still see difference, but it's not dramatic. We have limited time. I do want to leave some time for questions, but here I'll skip this application, but this is talking about how the display orientation matches or mismatch the text orientation and how that can generate effects. We have a demo at 5:30. So I think this one is interesting, right? We have two optical architecture. I'm an optical design person, and I do system design, and I use this metric to guide my design. If I just do 36 PPD versus 54 PPD, the cost of the engineer is very different, right? But in the end, this MTF chart, this is system MTF chart. Different chart means different frequency, 5 cycles per degree, 10 cycles per degree, and 15 cycles per degree. If we just focus on the 10 cycles per degree, you have the gaze direction. If you're in this field of VR and AR, you know what that means. The key point here is the two are matching, the two are equivalent. Right, so this means is you cannot just optimize for high PPD and suffer and let the fill factor suffer. You have to optimize all of them. Another place that we can put some investment is for free in software. We can, given a hardware system, we're limited in resolution, we're limited in fill factor. Certain things we couldn't do. What is the best way to render the graphics, right? And so certainly you have some filters. This is probably not very efficient. But the key thing here is you can go negative on certain pixels. And in the end, we can use the system MTF to render the best and to give the optimum result. So this is talking about the same thing, from the source image to the human eye and where you can apply this system MTF. And I do want to point out that if you just focus on the lens MTF, lens design, it doesn't really matter. I think fundamentally we're in VR today, we're limited by the display, by the sensor, unfortunately. So, use the system MTF to guide your whole system design, not just focus on the optics side. I'm not saying optics is not important, right? And I'm saying you have to look at the whole thing. So as a conclusion, hopefully we use one example to answer the question, how do we do this? Starts with a customer experience and how do we translate that into technology, into our products. And in my mind, there are just 4 things we have to focus on. Understand the experience metric. What do we want to create for users? Translate that to a math model for perception, for engineer metrics. And we talked about system MTF today. And then use that to guide the design, optical design or system design, lens, display, PPD, fill factor, graphics, also the camera side. And then engineering, we didn't talk about test metrology, but we spent a lot of effort how we implement this in test. But having all those, I think you can deliver anything. I think last one, do not focus on 0 to 1, deliver 0 to 1,000. I think that's my training from Apple and from Meta as well, and that's our focus. Thank you.